Okay. So, hi everyone. It's my pleasure to introduce our speaker for today, Evgeny Shinder from Sheffield. He will tell us about motivic invariance of birational maps.
Okay, thanks for the introduction. Hi, Vanya, finally. And thanks everyone for coming to my talk. I was giving similar talks in the past, but I think most people in the audience haven't seen it before. So I'm explaining a certain area I am advocating for. So there'll be 3 bits of motivation first, and then I'll explain some details. So first, motivation is the geometry of birational morphisms between threefolds. Specifically, we care about rationality of varieties, birationality between varieties, and also we may care about what is being blown up and blown down in a certain birational map. And we think of this as factorization centers. So a certain curve being blown up, we kind of call it a factorization center. It's not precise yet, but we'll be making this precise soon. Specifically for rational threefolds, we will be blowing up and blowing down points and curves. And if there's a single curve of higher genus that we blow up, when we connect P3 to X, we sort of think of this as the factorization center. Just to emphasize what I mean is, one of the interesting rational varieties is intersection of 2 quadrics in P5. So rationality construction is projecting it from a line which exists over a closed field. And then when you map this birational map to P3, the corresponding factorization center is a certain curve of genus 2 in P3. And we may ask the following question: is this rationality center determined by the threefold or not? And that's a quite subtle question. Specifically, as we will see today, and this is classical, that if you have a closed field of characteristic 0, then intermediate Jacobian recovers those centers that you blow up just from the variety itself. So if you know what the intermediate Jacobian is, probably you can guess how this would go. And more interestingly, over non-closed fields, there will be ambiguity in terms of the curves you blow up when you pass from P3 to your rational threefold. And we'll also see examples of this. And more generally, we can ask the same question for other dimensions, surfaces over non-closed fields, or let's say complex fourfolds, and we'll get various interesting things happening. So I guess the most acute question is that of K3s associated to rational cubic fourfolds. It's now an accepted wisdom that rational cubic fourfolds have an associated K3. And the question is to which extent it's well defined. And it's quite interesting and quite subtle. Any questions or comments about this? Okay, so we pass to motivation 2, which is structure of Cremona groups. Cremona group is the group of birational self-maps of a projective space. It has been studied a lot, but still most basic things are unknown. It's fully understood in dimension 2 over algebraically closed field when it's generated by a single involution, Cremona involution, 1 over X, 1 over Y, 1 over Z, and regular automorphisms of P2. So in general, much less is known, and there's not expected to be a simple structure of it. Specifically, results go in the direction of proving that it's big in a certain sense. So for example, Blank-Lamy-Zimmermann constructed infinitely many homomorphisms to Z mod 2Z, so showing that group is sufficiently big. So as we see, a lot of things is about, in Cremona is about involutions or Z mod 2, and the natural question was which Cremona groups or which groups with birational maps are generated by involutions. And so the answer is, from the Noether theorem, it follows that for P2, that's all right, over complex numbers, it is generated by this involution, and PGL3, which itself is generated by involutions, so it Cremona 2 over complex numbers is generated by involutions. And not much was known about this, specifically in dimension 3 or higher. Right, so yeah, so it's even complicated in for Del Pezzo surfaces over non-closed fields, and for higher dimensional projective spaces, there's no set of generators. And what I'll be talking about is more into abstractions to this kind of things rather than explaining that it is generated by certain elements. So, right, so motivation 2 is about a group of birational automorphisms, and we'll be proving that they are not generated by certain types of elements under certain conditions. And finally, a subject which is interesting to me, this is the motivic in the motivic birational map. So it's a baby version of motives, the Grothendieck ring of varieties. For every field, there's the following well-known ring defined by Grothendieck in the 60s. Generators are isomorphism classes of varieties over K, and relations come from cut and paste relations or scissor congruences. So for every closed Z, you impose one such relation. So it's a ring under induced by product of varieties over K. And relevant element for us is the Lefschetz class of A1. So that seems a very kind of naive thing to do, and also quite straightforward. But because it contains a lot of birational information, again, lots of basic questions about this are unknown. It's similar to Cremona groups, which is very easy to define but difficult to study. It's a bit similar here. Simple-minded group, but quite complicated. So the most naive question is, you have smooth projective varieties with the same class, are they birational or not? So it kind of looks like they should be from the description, but in fact, if you think of adding higher dimensional cells, there could be reasons for this to fail. What's currently known is that in characteristic 0, they are stably birational. So times by projective space, they become birational. And if we don't assume them to be projective, then this is false. Second question is about what does L annihilate? So we used to think that L is not a zero divisor, but then there were certain counterexamples to this. The same paper by Borisov, he constructs counterexample. So example of two varieties such that the difference is annihilated by power of a fine line. And for various rationality problems, and just out of curiosity, it's important to know what does L annihilate. So current examples of elements in the kernel of multiplication by power of L are differences of Calabi-Yau's K3 surfaces, genus 1 curves, and we'll see examples like this in the talk. And finally, it doesn't have immediate geometric applications. It's more curiosity, but whether this ring is torsion-free or not. It looks kind of torsion-free, but it doesn't follow from the definition. And we'll be addressing these questions on certain levels of the Grothendieck ring, where we bound dimension and filter it by dimension. We'll be able to answer some of these questions positively, even though in general the answers are unclear. Any questions or comments so far?
So far, so good. No questions, no comments.
Okay, excellent. So we go into the plan. So the plan of the talk, I'll define C of I, so the motivic invariant of birational maps with values in the Grothendieck ring of varieties or some variants of it. And then I explain this invariant for surfaces, threefolds, fourfolds, and state applications to Grothendieck ring. And finally, we discuss Cremona groups. So much of it is old work, which I have to finish and write down, but there will be some new results as well. Okay, so we begin with the motivic invariant. I just introduce where the category we work with, and the category is that of birational types. So we look at projective varieties over a field or smooth projective varieties, depending on the context. In characteristic 0, it won't matter. And morphisms are birational isomorphisms. So that's a natural place where birational geometry happens. And there are two essentially different ways to decompose morphisms in this groupoid. The first is the weak factorization theorem that between smooth varieties, birational maps are decomposed into blow-ups and blow-downs with smooth centers. And that's one powerful way to prove things about birational maps. And the other, which is totally different, is that of the minimum model program, where varieties are expressed as Mori fiber spaces, and morphisms between them are expressed in terms of compositions of Sarkisov links of certain type. So there's a kind of two different ways of factoring morphisms, and in the talk we'll be using both of them. Now I explain what is the invariant. It's kind of quite simple-minded, but as you'll see, it's an interesting homomorphism from the groupoid of birational types. So we start with birational isomorphism of smooth projective varieties, and we work with the set of exceptional divisors of this map. So exceptional divisors are irreducible divisors which are contracted in the sense that their image is not a divisor. In this kind of business, the important thing is to show that things are well-defined, but exceptional divisors are always well-defined, so there's no problem with them. And we'll look at exceptional divisors for phi and for phi inverse, as we'll see in the formula. So exceptional divisors for phi inverse are those which are created by phi. So here is the definition of the invariant. You have a birational map, and you look at those divisors which are contracted by phi, so in the right-hand side, and which are created by phi, so these are on the left. And we take the combination not in any Picard group or class group, but as birational types. So we record the birational types of these guys, and we put them into the free abelian group of on-birational types. So we note that there's certain symmetry that if you replace phi by phi inverse, then the formula changes the sign. So C of phi inverse is minus C of phi. And one of the points, which will be on the next slide, is that that's a homomorphism. So that's kind of right, the first part of being a homomorphism, that it preserves the inverses. I'll give some examples, and actually throughout the talk we'll be kind of discussing this invariant in various contexts. There will be a lot of examples. The first example in this weak factorization logic is that we'd like to know what our invariant is for a blow up or the inverse of the blow up, so the blow down. Specifically, if x tilde to x is a contraction, so blow up of a smooth subvariety, then exceptional divisor is a projective bundle over the center. So birationally, it's projective space times the center, C is the codimension. And then one weight counts with the plus, the other weight counts with the minus. So kind of the signs are defined so that if y is bigger than x, then it's a plus. So for example, x is smaller than x tilde, so this is negative, and in the other direction it is positive, but it's just a convention. So a single exceptional divisor recorded with sign plus here and sign minus here. And kind of the opposite example is when you don't contract any divisors at all, either way. So if you have pseudo isomorphism, then the invariant is 0. So once again, for every birational isomorphism, we compute divisors which are contracted, divisors which are created, and look at the corresponding combination inside the free abelian group of birational types. So as I said, the key fact about this invariant is homomorphism under composition. So as soon as you have two composable maps from between varieties of the same dimension, then the property is that C of the composition is the sum of the two invariants. So in particular, if you look at birational isomorphisms from X to itself, then you get a homomorphism to this free abelian group on birational types. So how one proves this? One computes exceptional divisor of the two compositions, so psi phi and phi inverse psi inverse in terms of the exceptional divisors of everything else, and using inclusion exclusion. So it's kind of not immediately obvious because it could be that a divisor is created and then contracted, but it's all counted in this formula. So far, I haven't explained that this invariant is never zero, and probably this is why it wasn't considered earlier, because this kind of thing looks a bit like zero, that you look at what you create minus what you contract, and you don't expect to get something interesting, but it is actually non-zero, as we will be seeing. Some remarks of where it takes values is the following. So we're looking at birational classes of these varieties, and they belong to this free abelian group on birational types. For smooth projective varieties, exceptional divisors are ruled. So in fact, the image belongs to some subgroup of this, which is the image of n-2 birational types times P1. So all the exceptional divisors are ruled. So we can sort of try to divide them by P1, but we shouldn't do this because in general, these maps are not injective, as varieties can be stably birational without being birational. So we should consider them here, the classes, not in here, in general. And then another remark is that sometimes we want to pass to stable birational types where, where we look at only classes of stable birational isomorphism and look at this kind of composition. And for most of the talk, this weaker invariant will be sufficient, just stable birational types of the exceptional divisors. Any questions or comments? Yeah, you can ask anytime, and I also am trying to monitor the chat.
So far, no questions in the chat.
Okay, excellent. So we, as I promised, we'll be doing examples. So here is the basic example. I mentioned Cremona transformation, 1 over x, 1 over y, 1 over z. And when you think of exceptional divisors, it's the familiar graph with 3 lines intersecting in 3 points. So if we look at those inside the stable birational types, each P1 counts as 1. So we get 3 minus 3. So there are 3 exceptional P1s both ways. And when we quotient out by P1s, we get 3 minus 3, which is 0. So for the standard Cremona transformation, the invariant is 0. So as I said, 1 is stable birational type of a point or projective space. More generally, if you think of surfaces over a closed field, again, nothing interesting is happening. So here is why. When we count divisors created minus divisors contracted, or the other way around, we essentially, in this case, look at the difference in the Néron-Severi group. So if you blow up a point, Néron-Severi group goes by 1, and if you contract a P1, Néron-Severi goes down by 1. So anyways, from here, decomposing these maps into blowups and blowdowns, it's easy to see that the invariant is always the difference of the 2 ranks of the Néron-Severi, and nothing interesting happens. In particular, for self maps in this context over closed fields, we get a 0 invariant. So whatever goes up should go down. So for surface over closed fields, there's nothing interesting. And the first interesting situation is will be for surfaces, but over non-closed fields. This is where we have rich birational geometry and where points can be closed, but not rational points. So here we can make the invariant a bit more precise as follows. So we're looking at surfaces, and all our exceptional divisors are ruled over zero-dimensional smooth schemes. So we can, in this case, divide by P1. So Z is just the connected components of this scheme. So Z is well defined here, the center. And then we can consider the invariant as taking values in zero-dimensional varieties. So what are zero-dimensional varieties? These are basically over perfect fields, combinations of finite field extensions. Usually we don't think about zero-dimensional varieties, but here we do, and it's a kind of just Galois theory over K. So once again, we're recording Galois orbits which are blown up versus Galois orbits which are blown down. And it's a non-trivial result that this invariant is still vanishing in the following sense. So if you have two surfaces, X and Y, and look at birational maps between them, and record what's blown up, what's blown down, take the alternating sum, and then the value is independent on the choice of the map. So why I'm saying it's a vanishing result, because when you have the same surface and you look at any self-birational map from X to itself and record this invariant C, you get the zero map. So explicitly, this means that for every self-map of X to itself, when you decompose it into sequence of blow-ups and blow-downs arbitrarily and take all the centers with the signs, you get zero. So all the Galois orbits contracted correspond to Galois orbits created. And I want to emphasize this non-trivial theorem because there's no way to read off these Galois orbits just from homological data. So when I think of Galois action on neuron severi or some invariant like this, Chow motive, but it's not fine enough to distinguish Galois orbits from their linearization. So kind of in my talks, I typically challenge people to try to find an easier proof. So our proof goes through classification of surfaces and Sarkisov links. So essentially, we have to check all Sarkisov links between all type of Mori fiber spaces in dimension 2. There's certain simplification in the proof, but we still have to check several. And this is a result which depends on classification. We don't know of an abstract reason for why this is true. And it kind of points in the direction of the invariant can be non-zero in other contexts, and this is where we'll be getting soon. Before that, let me explain consequences for the Grothendieck ring. So I introduced in the introduction Grothendieck ring as a certain ring with generators and relations. And to study it, we may consider a truncated version. Specifically, we look at only varieties of dimension up to D. So generators, isomorphism classes of varieties dimension up to D, and relations are the same cut and paste relations for this kind of varieties. And there's partial defined product, which we won't use very much. So what are small dimension cases? Varieties of dimension up to 0 are those Galois orbits I was talking about. And relations are just disjoint unions. And varieties of dimension 1, because every smooth projective curve has a unique, as every curve has a unique smooth projective model, there's a splitting into points, the first summoned, and isomorphism class of smooth projective curves. There's no interesting birational geometry of curves, therefore that's a trivial direct sum. In general, Grothendieck ring is the limit or the co-limit of these maps. So we have varieties of dimension up to D, mapping into up to D plus 1, and we take the co-limit, we get the Grothendieck ring. And as we'll see, the maps are not injective, and that's quite interesting. This is about adding this higher dimensional cells to make equalities where there were no equalities previously. However, so what is true in dimension up to 2 is the following. So all the questions I raised about the Grothendieck ring are true on this level. Specifically, we have such exact sequence. So in some sense, equality of classes here is about their birationality. So equality of classes means that highest dimensional components are birational. And furthermore, because this is a free abelian group, and this is a free abelian group, this whole thing is also a free abelian group, so there's no torsion, and multiplication by L is injective. There's no kernel. So kind of, if we want to study growth-decreasing varieties, we can study it level by level, and essentially this result about motivic invariant for maps for surfaces is saying that growth-decreasing varieties of dimension up to 2 over perfect fields works as expected. There are no surprises here. And we'll see surprises in dimension 3 already. So I think there's some K-theorists in the audience, and just for K-theorists, the way I think about this, so this K0 of variety is a bit like K0 of a scheme, and then this filtration by dimension is a bit like associated graded Chow groups. And that's quite interesting and not well understood, this filtration and the factors. Now I explain threefolds. So we go up in dimension. We start with complex threefolds where again, the invariant is 0, which means that if you look at a self-map from rational self-map from X to itself and look at curves you blow up, blow down, there's a bijection between those centers. And maybe I won't go in details over the proof. I'll just say it uses intermediate Jacobian. So as soon as you know what blow up does on intermediate Jacobian, plus Corollary theorem, you can recover the centers you have blown up. And specifically from X to itself, there will be no difference in the centers you blow up and centers you contract. And as a consequence, similarly to the previous slide, we have full control over K0 varieties of dimension up to 3 over complex numbers. There's natural filtration, it's a torsion-free thing, and the quotients of filtrations are birational types. So here is where the invariant is non-zero for the first time. We're looking at threefolds over non-closed fields, and then later on we'll look at fourfolds over closed fields. They have similar flavor. This is a bit more arithmetic. So what's the same as for complex numbers? So we have weak factorization characteristic 0. There is intermediate Jacobian for rationally connected threefolds. And the Corollary theorem holds for curves, but not of all genus, but only starting from genus 2. So why Corollary theorem doesn't hold for small genus? So for genus 0, all rational curves have the same 0 Jacobian, but there are a lot of different rational curves over non-closed fields, conics. And in genus 1, genus 1 curves are not determined by the Jacobian either, because there are twisted forms or torsors over this Jacobian. So Corollary theorem cannot hold for genus 0 or 1, but it does hold for higher genus. So as a result, we see that higher genus curves can contribute by the same proof, but conics and elliptic curves, or more precisely genus 1 curves, can contribute, because there's no way we can read them off from the Jacobian of the threefold. So we don't know any examples of genus 0, namely whether you can have a self-map from a threefold to itself where you blow up one conic but contract onto the other conic. We don't have anything like this, but we do have an example where you blow up a genus 1 curve and contract onto a different genus 1 curve. So what's different from dimension 2 to dimension 3? Dimension 2, we showed that invariant is 0, and we used classification of Sarkisian links. So here we have no such classification, and therefore it's not easy to see what exactly is in the image of the invariant. And as another consequence, when we look at growth-decreasing varieties for dimension up to 3, already its structure is more interesting, and L is a 0 divisor for the first time in this version, where we look at 3-dimensional varieties and a perfect field, non-closed field. So what I'll be doing, I'll be explaining now this example, which is in boldface, one known examples where something interesting is happening. So I'm supposed to present a non-zero invariant. Is there, right, excellent. Yeah, Dan is asking a question whether the two genus one curves have the same Jacobian in order. Yes, they are torsors for the same, we're getting there, so it was good, well-timed question. We are looking at Jacobians of a single genus one curve. So we're looking at degree 5, which is the first interesting degree. So we're looking at non-closed fields such as rational numbers or any other number field, and we take a elliptic quintic with no rational points. And then the other curve, its partner, is peak 2. So it is the Picard variety of degree 2 divisors on C. So they are twisted forms of each other over algebraic closure. They're isomorphic, but usually they're not isomorphic. So unless you have a point or there's an exceptional case of special J invariant, this will be two different curves over K. Yeah, and so here we have the first example of the fact that invariant computes something useful is that we are producing birational automorphisms of P3, so elements of Cremona 3, such that the corresponding invariant is the difference of these two torsors, C and C prime. And in brackets, I note that in general, they are not, so they are not isomorphic, and so the difference is non-zero by the standard argument that they cannot be birational unless they are isomorphic. So when we have to prove something like this, we need to present a geometric construction. And to find such geometric construction, we need to look at links between Mori fiber spaces or Fano varieties in dimension 3. We start slowly, so we start with a standard projection from Q3 to P3, projection from a point. And then one can see that because the centers on both sides that we blow up and blow down are all rational, so point and a rational curve, the invariant C of this map is 0. There are no non-trivial centers in terms of birational geometry of the centers. However, we want to compose this gamma with another morphism, which is a certain non-standard rationality construction for a three-dimensional quadric. So this is kind of, this two lines are more for, so this line is more for Fano experts. So there are certain Mori-Mukai links, Sarkisov links between Fano threefolds. There are finitely many of these links, and they both start with, so they start with two Fano threefolds of index bigger than 1, and there's a blow up and blow down connecting them. Here, 24 in the middle means that there's a certain Fano of degree 24. And then if we look at the construction, one way we blow up the curve C, and what we contract is the set of 2 seconds to this curve. And when we think of 2 seconds, it's birational, stably birational to this peak 2, because to specify a 2 second, we have to specify 2 points on the curve. And over closed field, it's not a big deal, but over non-closed fields, that's not the same curve, but it's second Jacobian. So if we compose the two maps, then by the additivity of the invariant, we get 0 plus this difference. So we do get a self map from P3 to P3 with the given properties. So there are a lot of interesting self maps with non-zero invariant. So Mori-Mukai don't emphasize that these are different curves. They work over complex numbers, but over non-closed fields, one sees that the curves are what I explained. So in principle, we would want to know the image of our invariant and what can we use, like which maps can we distinguish. But in fact, as I'll be showing at the end, such non-vanishings already have interesting applications to Cremona groups because it shows existence of a certain elements inside Cremona groups. So, right, so this was a bit ad hoc. Let me now explain the new slide, which is kind of makes infinitely many constructions of similar things, but is a bit less explicit. So specifically, more generally, let's look at still a genus 1 curve of degree D. And let's take another curve, C prime, which is now a twisted coprime twisted form of the curve C. So previously it was peak 2 for degree 5. Now it's some other coprime Jacobian. So these are twisted forms, and they are derived equivalent. This was going back to Bridgeland, and then in this particular form, it's an Antioch-Russian word. And furthermore, all Fourier-Mukai partners, so derived equivalent varieties to C, are among those other twisted forms. So basically, the story here is just about coprime Jacobians or coprime Picard varieties. And a natural question is, so are these curves L-equivalent in the sense that is the difference annihilated by power of a fine line in the Grothendieck ring? So this is true for D equals 5, as we proved with Zhang, or also, which is proved by the slide earlier. So kind of we ask, what do these Jacobians have in common geometrically? And the answer is the following. So we claim that, I claim that there exists for every such pair, C and C prime, a birational automorphism of PD minus 1. So D was the degree of the curve, minimal degree of a closed point, such that it contracts one of them, blobs one of them and contracts exceptional divisor onto the other one. So they are partners in the sense of being exceptional divisors for the two sides of a self map on a projective space. So note that D goes to infinity here. So kind of for every D, it's something bounded, but altogether that's infinitely many interesting examples. So the proof uses not very well-known work of Tregub from the 90s, where he constructs interesting birational maps by blowing up elliptic scrolls. So he does a little bit of moduli space of sheaves on elliptic curves, and he explains a certain map and what it blows up, what it contracts. It's not clear over which field he works, but it seems like that it doesn't matter, that as soon as one has a degree D genus 1 curve, one can run the construction and get various maps like I want. So our invariant is not only non-zero, but it connects, it's strongly non-zero and connects over non-closed fields, torsors to each other. Now we're going into a similar story, but over closed fields. So we're looking at, instead of genus 1 curves inside threefolds, we're looking at K3 surfaces inside P4. So here, again, we want to produce some non-vanishing, so we need to use a certain construction of an interesting birational self-map. And the construction goes to Hassett Lai in 2018. So we start with a K3 surface of degree 12 on Picard rank 1. So kind of, as soon as we have such a thing over our field, we can run the construction, which follows. Then there's a partner of it. There's a unique Fourier-Mukai partner, K3 surface of degree 12 and rank 1, which is derived equivalent to it. So the claim, and when this originally appeared, is that these two classes are annihilated by power of a fine line in the Grothendieck ring. And specifically, one of the construction due to Hassett and Lai goes as follows. The claim is that there exists a self-map from P4 to itself, so element from Cremona 4, with the following factorization into blow-ups and blow-downs. First, you need to blow up 3 points, so they work over C. In general, this is an orbit of 3 points. And then one blows up X, and it's symmetric. So on the other side, one contracts y and then contracts onto 3 points. And this is the map. So in general, this belongs to an area of classifying certain simple type maps between Pn and the self, such as one blow up, one blow down. And here it's kind of two blow ups, two blow downs, or instead one can blow up single. Yeah, I suppose the image of the K3 we blow up here is a singular one. Instead, we can try to blow it up. But yeah, so this is one of the special Cremona transformations there is. And just by computing the invariant in the way I was explaining, so it's additive, and this arrow on the left cancels the other arrow on the right, we see that the invariant for this map is x minus y. So x is the divisor, is the stable birational type of the new divisor, which is created by the first blow up, and then y is the stable birational type of the divisor, which is contracted on the right. So the difference is x minus y. And indeed, like the same reasoning as before, for elliptic curves shows that the classes are different as soon as these K3s are not isomorphic. So again, we would like to know which K3s are related in general in this kind of fashion, and specifically for what do we get for cubic fourfolds. This is not clear at all at the moment, but currently we're in a situation where examples are worth collecting. So we're moving to the final section of the talk, is where we'll be using those examples. Before that, we need to do even higher dimensions. So I explain dimension 3, dimension 4. Higher dimension we can do non-vanishing, and higher dimension we can do in kind of a lazy fashion. So we start with the rational map from the previous slide, from P4 to P4, and then we can multiply it by identity on any other variety, for example, on a projective space itself. This way we create a map from a higher dimensional projective space to itself, and then one can see that the corresponding invariant simply multiplies the old invariant by the base we take, so by projective space. And so if it was non-zero previously, it's still non-zero. So it's the same, sort of the same map. So it's you multiply by projective space, and the invariant is still non-zero because those two K3s were not stably birational, because K3s cannot be stably birational unless they are isomorphic. So this is kind of one thing we can do. We can just spread out a single example into all dimensions bigger than the given one. Or there are other examples which we can get from the literature, such as Calabi-Yau threefolds in 5-dimensional rational varieties. And again, we can show that our invariant can be equal to difference of two non-isomorphic derived equivalent Calabi-Yaus. It looks like the values we obtain are a lot about Calabi-Yaus, but it's not necessarily the case. So I don't explain this in detail, but in fact, genus 1 curves we were constructing earlier can be spread out into elliptic surfaces. And then formally, by passing between curves in threefolds and these elliptic surfaces and fourfolds, we can obtain elliptic surfaces. So K3 we can get or rational or actually elliptic, Cudery dimension 1 as these differences. So the role of Calabi-Yau-ness here is not very clear. It may not be important. I'll explain now the applications to Cremona, which I alluded earlier, where we'll exploit the examples constructed, even though we don't know the full image of the invariant, but we use the non-vanishing to show that certain things about Cremona groups just cannot be true. And these methods kind of are the only ones which exist so far to tell these kind of things. So previously I explained that one has constructed, Blank-Lamé Zimmerman have constructed infinitely many homomorphisms to Z mod 2 from the Cremona group. And in general, there was this feeling that maybe abelianization is to torsion, or the whole group is generated by involution. But now we'll be showing that it all fails. So we need to have a field for which we have an vanishing example. For example, we can take complex numbers. So a large enough field will work. And then we may run this Hassett-Lie construction, and it's not just for single pair of K3s, it's a family of Picard rank 1 degree 12 K3. So it's the same cardinality as the base field we work with. Yeah, and so as the first application, we obtain the following. So as soon as we're in this situation, we can take complex numbers here, or another sufficiently big field. We construct infinitely many homomorphisms to Z, or in other words, homomorphism to direct sum of the Z's labeled by a set of cardinality equal to the base field. So, right, how do we get this? So basically, we will project our invariant, which goes from Cremona to this free abelian group on birational types, onto the differences of K3 surfaces we have obtained in Hassett-Lie maps. So we separate a certain big subgroup inside the values group, which has this form. And for that, I explained that we have a family of parameters for those K3 surfaces. So we can construct this, or formally by passing to abelianization, because the term on the right is a projective Z module, we have a splitting over after abelianization, and we get that Cremona M starting from 4 over most field has infinite rank free abelian group as a direct summand. So this should be contrasted with cases which were known before, such as in dimension 2, Noether's theorem implies that Cremona 2 is generated by involutions, and in fact, one can show that abelianization is 0. Now, for real numbers, Susanne and Zimmerman proved that it's a direct sum of Z mod 2, so it was actually two torsion in that case. And the result of Lamit-Zimmerman I was alluding to implies that one can show that infinite direct sum of Z mod 2 sits inside the abelianization. So in some sense, results I'm talking about are orthogonal to those results. It's a different type of elements inside the same Cremona group. Now I speak a little bit about regularizable birational automorphisms, and I explain a question which goes back to Vanya in 2000s. People who study Cremona groups classify elements in certain types, and one important type is finite order, and the weakening condition is regularizable. Regularizable means it's conjugate to a regular automorphism. So you can change the model such that your birational map becomes a regular one. And it's kind of just looking at this definition, not clear which ones are regularizable, which ones are not. A folklore simple lemma says that elements of finite order are regularizable, but then there are ways to show that not all the elements are regularizable. And then Vanya was asking a long time ago, which groups of birational automorphisms, specifically Cremona groups, are generated by regularizable elements. And as an evidence, so he kind of meant probably this is the positive way, and as an evidence he listed surfaces and threefolds, mostly without having a lot of birational automorphisms which do satisfy these properties. So as a result of the invariance, everything is answered negatively. So in the cases I have introduced, so I'll list them below, Cremona is not generated by elements of finite order or PGLN+1, and elements of finite order or regularizable elements or involutions. So none of these in each of the cases I was talking about earlier. So either n equals 3 and some small fields, such as any number field, or n starting from 4 and big fields, for example, complex numbers. So what's interesting and what I say in every talk about this is that the question that Dolgachev has probably been asking about is open. So Cremona C over complex numbers is when our invariant is 0, and yet it's unclear whether the group is or is not generated by involutions. So what's the proof of the corollary? It kind of follows nicely and simply using what I was talking about earlier. Let me just do this computation that basically, let's show that regularizable elements have vanishing C invariant. And for that, by definition, it's conjugated to a regular element. Regular element has no exceptional divisors either way. So it's a 0. And then because values are in the abelian group, the whole thing is 0. So basically, as soon as you have values in the abelian group and you vanish on regular elements, you also vanish on regularizable elements. So definitely your group cannot be generated by regularizable elements, because then the invariant will always be 0, but it's not in the cases I list. All right. Any questions or comments?
No.
All right. So regarding Cremona 3 of C, I guess it's interesting to compare it with birational automorphisms of a cubic threefold. So none of these groups is understood, neither birational automorphism of P3 over complex numbers, nor birational automorphism for cubic over complex numbers. There's this dream to, by distinguishing them, we prove that cubic threefold is not rational. And it would be very exciting if one of them was and the other wasn't generated by involution. So for example, for cubic threefold, it feels that there are slightly fewer birational automorphisms. The birational group seems kind of more rigid than for P3. And on a cubic threefold, lots of birational automorphisms we can construct are actually involutions coming from fibrations or coverings. So it could be that for a cubic threefold over C, birational automorphisms are generated by involutions, but for P3, they are not. This would be quite interesting to see. But it's not clear how to approach either of these questions currently. So we are wrapping up. Conclusion. So I introduced the motivic invariant C in the Grothendieck ring of varieties or versions such as Z on stable birational types. And it records centers we blow up or blow down in factorizations. It's 0 in small dimensions, such as for surfaces of perfect fields or complex threefolds, but it's not 0 in all other contexts. And this has applications to what we believe or don't believe about Cremona groups. So so studying the image of C is important, specifically which K3s or which genus 1 curves you can get an image. And this has implications for Grothendieck ring if we're interested with this, or Cremona groups if we're interested in this. So I'm mostly focused on Cremona groups, but in fact, if you remember, the proofs of the results at the end were taking P3 or P4 and multiplying with a higher dimensional projective space. Instead, we could multiply by another rationally connected variety and get similar results, but the results are most concise and clear for those Cremonas. So in principle, one dream would be to bound the image in some sense. If you remember, early on, I was saying that certain things go to infinity, but when dimension goes to infinity, it would be interesting to see that in a given dimension, let's say for P4, you look at self-birational maps, and you look at the differences between what you blow up and what you blow down, and whether you get only bounded set of data. Or, for example, the other extreme would be that you get K3s of infinite degrees appearing without constellation in those self-birational maps. Okay, so I think that's more or less it. Thank you for your attention, and you can ask questions now or also ask me by email if you'd like to.
Thank you, Zhenya. Thank you very much for excellent talk. Any questions?
Could I ask a question?
Sure, Peter, yeah.
I would like to understand a little bit, maybe it was mentioned, but I couldn't figure out. What is the relation of the C variant to that open question about the torsion in the glutamic ring?
Yes. I'll have to scroll all the way back.
Yes.
So, right, and like the glutamic ring has a filtration and like vanishing of the invariant C was telling that the cokernel here, going from level 1 to level 2, is a free abelian group. And this allows us to deduce that the middle term is also a free abelian group because the sequence splits as the term on the right is project is free. So this vanishing for surfaces was implying that up to level 2, we have no torsion. And similarly, for threefolds over complex numbers, we have no torsion here as well. So kind of torsion is controlled because torsion is controlled by the quotients we obtain, and the quotients are controlled by this invariant, if this makes sense.
Once again, torsion is controlled by the quotients, and
by the quotients,
okay,
by the invariant. Yeah. So like
yes,
you see, it's a bit like dimension filtration on the K theory, right? And over there, yeah.
Okay, and are there some references I could see these things about the problem, about the torsion problem in the glutamic ring, and eventually related with the C invariant?
So the C invariant is we are hoping to write it down soon. Yeah. That's partly why I want to give this talk is to finish this bit of the project. For the torsion, there was a math overflow question. So I think we attribute this in the paper. So I'll just show you the questions. I didn't attribute it in the talk. So the first two are well-known questions, and the last question is just asked by math overflow, and then people are saying that it's completely unclear.
Do you know who asked it?
Maybe it was even a user with a nickname, so maybe it wasn't. Yeah, I don't remember. No.
Okay. Okay.
Thank you.
Thank you very
Zhenya.
much.
Thank you, Peter. Any other questions to Zhenya? Yes. Yeah.
Right. So Birkar boundness. Yeah, excellent. So
how to use Birkar boundness to bound C?
Yeah. So like this is what we do for surfaces. We look at all Mori fiber spaces and all circuits of links between them, and it allows us to show that the invariant is 0. And we're thinking of for threefold case that it's non-zero, but all the data is bounded in some sense, right? So Mori fiber spaces are bounded in some sense, and the links are bounded in some sense. And it's a bit difficult to make explicit in which sense they're bounded, because not in every naive sense it's true, but one hopes that one can deduce the boundness of the image from that. It's like a question of what kind of things can you blow up on a chosen Fano to still get a link with this center, right? Without canceling your center at the same time. So certain symmetric links will not be allowed, like when you blow up lots of points on the fibers, but then contract the same thing straight away. This doesn't matter. But what matters if when you blow up something and then suppose get to Mori fiber space or something. Yeah. So maybe it's a question also for Vanya, because similar things were used in the paper by Vanya, Prokhorov, Blanc, and Duncan.
Yeah, about the genus unbounded. But I think in all your examples, this phenomenon happened when you blow up something close to rational or close to Calabi-Yau. Yeah, so so which probably answer this question. Yeah.
So the relevant case is this genus 1 curve. Vanya. So I'll just show you. The genus 1 curve. So this one. So there's this link, and we try to look at other links, but it doesn't seem like there's anything else which is going on there.
Yeah, but exactly what you mentioned about the sterility for curves of a non-closed field. So in some sense,
Yeah. But the genus 1 curves we can't control, and kind of the question is whether between three folds.
but you can think this they should sort of expect some kind of boundedness for them.
Yeah, that's
So,
what we think, but it's
but
not
again,
completely clear.
on intuitive level.
Yeah.
Intuitive level.
Mm-hmm.
Okay, thank you. Nice question. Any other questions to Zhenya? Okay, if no, let's thank Zhenya again for excellent talk. Okay, let's stop recording. Stop recording. Yeah. Did you stop?